Okay, so this will be the first example problem we do really about virtual work. So you can see I want to find the displacement at C, which just happens to be the midpoint. And I have a value for I, 240 inches to the fourth, and a value for E, which is pretty close to steel. So remember, if we're going to do virtual work for this particular problem, I'm going to have to write an equation for moment that's valid across the whole structure, and then a set of equations for the virtual load. So let's start with the what I'll call the real moment first. So to find the real moment, I'm going to need some reactions. So let's start by assuming I have a value here for AY and DY. Let's find those reactions. So to find my reactions, I think I'll start by summing moments about D. That should help me find AY. And then we can sum forces in the Y direction. We can find DY. So first, if we sum moments about D, make sure we're in equilibrium. I'm using right-hand rule, so this 16 kip force creates what kind of moment about D? Positive. So I got a force of 16 kips and a distance of, looks like 30 feet. And then my reaction at A creates what kind of moment about D? Positive or negative? Negative. So that's AY, and that has a moment arm of 40 feet. So it looks like AY is going to be 12? 12 kips. And then if I sum forces in the Y direction, I should be able to find DY pretty easily. So again, summing forces in the Y direction, making sure it's in equilibrium. I assumed AY was up, that DY was also up, and that that 16 kip force was acting down. So it looks like DY is 4. Any questions about that? So next, that I have all these reactions, I want to write equations for moment. Can I write a single moment equation for this beam? No. So I'm going to need to write one that's valid from A to B, which is 0 to 10, and then a second equation that's valid from B to D, which would be from 10 to 40. Everybody see that? So I'll just call this section real moments. And we'll start with the first section. So this will be where X can go from 0 to 10. So I'll cut the structure at some distance X in that range. We know AY, already solved for that. That was 12 kips. And then I'm also going to assume positive bending moment. So from that, I can easily find the internal moment. So I'm going to sum the moments at this cut that I made using method of sections. Make sure it's in equilibrium. The internal moment is positive, and the moment about the cut from the reaction 12 is negative. So that's pretty easy to find. Looks like the moment is equal to 12x. Any questions about that? Pretty straightforward. So let's do the next one. Let's make a cut somewhere here between B and D. I think it's going to be easier to work the right-hand side. So this will be the moment that's good from 10 to 40. So again, I'm going to make a cut. That's the right side, so I'm going to have my reaction there is 4 kips. So again, the distance to the cut is x. So what's this distance of this little segment? Be the total length minus x, which is 40 minus x. And then again, I'll assume positive bending moment at the cut. And I just need to solve for that. So again, I use method of sections. Now that I've done that, I'll just sum the moments at that cut that I made. Make sure it's in equilibrium. This internal moment with my sign convention is negative. And then this 4 kip reaction is going to create positive moment. 4 kips times a distance of 40 minus x. So solving for the moment, I guess I'll just go ahead and run that through. So I'll end up with 160 minus 4x. Now I can check these, right? I know the moment at 2 places. What's the moment here at A? 0. And that's at x equals 0. So I use this equation. And you can see if I put in x equals 0, I get 0. So that checks. What about here at D? I also know the moment is 0. That's at x equals 40. So using my equation for that range, plug in x equals 40, you can see I get 0. Now the one other place to check would be at the point they share, which is x equals 10. So if I put in 10 here, what do I get? 120. If I put in 10 here, what do I get? 120. So I feel pretty good about these moments. So the next thing I need to do is I need to do my virtual system. Now to do my virtual system, I have a completely different problem to solve. So I'm going to first draw the frame. I'm going to have a reaction at A, just like I had before, and a reaction at D. But what is the load on the virtual beam? Remember, I'm trying to find the displacement at C, which is right here in the middle. So now I'm going to have a virtual load of 1 right in the middle of the structure. 20 feet and 20 feet. Everybody see that? So I'm going to have to write how many virtual load equations here? 2. One that's from 0 to 20, and a second one that's from 20 to 40. I'm going to follow the same strategy I did here. I'm going to cut in the first segment and use the left side, and then when I cut in the second segment, I'm going to use the right side. So I'm going to need both my reactions to get started. I think we can probably already guess what the reactions are going to be. What do you think they're going to be? A half and a half. If you wanted to shortcut that and you felt good about it, you can. I won't do that. Just to be complete, I'll go ahead and solve the problem. So I'm going to sum moments about D, make sure I'm in equilibrium. And when I do that about D, the unit load 1 creates positive moment, and AY creates negative moment. And as we suspected, when you solve for AY, you do get 1/2. And then if you sum forces in the Y direction for this free body, and also make sure it's in equilibrium, you're going to find that AY acting up plus DY acting up, 1 is acting down. And again, as we talked earlier, you find the reactions. So now that I know those, I'll follow through with the strategy we discussed. So the first one will be looking for the virtual moment between 0 and 20. So I'll cut the structure, and we will look for the internal moment. Now this is the virtual moment, so I'm going to use the lowercase m. And then I know my reaction at AY is 1/2. It doesn't have a unit because our virtual load doesn't have a unit. And again, that will be at a distance x. So when I sum moments at the cut and make sure it's in equilibrium, what do I get? Well, I have my internal moment, which is positive, and this force of 1/2 creates negative moment with a moment arm of x. So my virtual moment is just x over 2. And now I'm going to find the moment, the virtual moment that is valid from 20 to 40. So I'm going to cut it and look at the right-hand side. So at that point I'll have the reaction at dy, which we solved for as 4 kips. Oops, sorry, 1/2. Looking at the wrong one. 1/2. And then I'll have my internal moment there, positive. So again, up to the cut from the left side is an arbitrary distance x. So what I'm left with on the right-hand side is the length minus x, which should be 40 minus x. And when I sum moments for this free body and make sure it's in equilibrium, well, what do we get? Well, we get the internal moment is negative. The moment created by the 1/2 force about the cut creates positive moment, and it has a moment arm of 40 minus x. So when I solve for the internal moment m, I'll go ahead and I may just leave that 1/2 there. So I'll just say 1/2 40 minus x. Now before we move forward, we can again check these. So in this virtual system, we should also know something about the moment A and D. Do we know what's the moment at A? It's a pin connection. Should be 0, right? So if I put in x equals 0 here, I do get 0, so that's good. At D, which I know is a pin, I should also get 0 moment. That's at x equal 40. And again, if you come over here and you put x equal 40, 0. Now these two share a value at 20. So when I put 20 here, I get 10. When I put 20 here, I get 10. So it seems like everything matches up. So I feel pretty good about my moments. So any questions about that? So really, you've done the hard work, I think. And now all we need to do is piece them together and form what I like to call the virtual work equation. So let's do that. Drop my pen. Hang on a second. Okay. So I'm going to flip this up. And so what I'm now going to write here is that our displacement y at point C is normally the integral over the entire length, which is 0 to 40, of the real moment, the virtual moment, divided by EI dx. Now, we can't do the integral over the whole length because our virtual moment varies, and real moment varies, and our virtual moment varies. Okay, our real moment varies from what? It's got one equation from 0 to 10 and a different equation from 10 to 40. The virtual moment goes from 0 to 20 and then from 20 to 40. So we're going to have to break this thing up into 3 segments. So we're going to have the integral from 0 to 10. We'll have 2 equations for that, and then it'll change from 10 to 20. Why? Because the real moment changes. And then we have to stop at 20 because the virtual moment changes. But then from 20 to 40, the equations do not change. Oh, I left out my differential distance. So that's what we have to do. Kind of messy. But I think we can do it. So let's go back here. I'm going to go ahead and factor out the EI and put it up here on the front and say that that's going to be multiplied by the whole thing. So the first integral from 0 to 10, let's see, my real moment is 12x. My virtual moment is x over 2. So I've got 12x times x over 2 dx. You can see that's not going to be very hard to integrate. My second expression from 10 to 20. So let's see, 10 to 20. So now this is my real moment, 160 minus 4x, but this is still valid for my virtual moment. So I'll have 160 minus 4x, and the virtual moment is unchanged. And then the last piece goes from 20 to 40. So this is my virtual moment, 160 minus 4x, and this is my real moment, 160 minus 4x. This is my virtual moment. So I still have 160 minus 4x. And then I get, what was the virtual moment again? I'll have to flip back, I lost it. 40 minus x and a half. So it's got 40 minus x. I'll put the half up front, dx, and then I'll close up my bracket for the divided by EI. You can see why on an exam, this would be good enough for me. You can just stop here. Because you could spend a lot of time, valuable time on the exam, just doing all these tedious calculations. And there's so many places to make little mistakes along the way. So for me, most times, this is good enough to stop. So anybody have any questions about this? What I'll do, I'll go back in my office and I'll actually do these calculations and divide by EI and give you a numerical value. So when you see this online, in the PDF of this, you'll see the solution. If you choose to look at the video, it would stop pretty soon at this point. All right.